Okay, so let's get started. This is a talk about Fs2. And Fs2 is a purely functional streaming I/O library for Scala. And hopefully all those words will make sense by the end of the talk. But even though this is like a streaming library, what this talk is really about is actually control flow, so declarative control flow. So I hope I can show you how streams are not only useful for like streaming, but also sort of build your program in a nice, composable, declarative way. So who am I? My name is Fabio. Senior software engineer, currently in the financial industry. And you might know me from, like, you know, if you like hang out in the Scala FP ecosystem. I'm one of the maintainers of Fs2, and I help maintain H3.4s, Cat effects, and a bunch of other stuff. Yeah, that's it. So I had a whole section about what PureFP is and like why Future is not PureFP, but we're running out of time, and like I think you all know by now, so it's good. Let's skip it. Yeah. Boom. So boom, Cat effect straight away. So Cat effect is a project that basically exposes an I/O monad similar to the one that John has just finished talking about, and the shape of this type is just I/O of A. So if you know Haskell, it's kind of like the Haskell I/O. If you know Future, it's just kind of like Future, but better and pure. So what's the semantics of this? So this I/O type represents a computation that can either produce one value, or fail, or never terminate. When I say produce, obviously I mean when run. So this is just a data type. Returning this thing and manipulating this thing is just like manipulating option. But when you actually go and run it, it will do this thing. And the key property of this type is that it's referentially transparent. So that means that if you, that was what the previous section was about, but it means that you can replace a variable for its bound value without changing the meaning of the program. So it turns out this is like actually super powerful and super useful. And the reason why it's so useful is because it's compositional. Since you can always replace an expression for its bound value, it means that there's no context being carried around. Like, all a computation needs is its input, and all it does is its output. And that means you can reason about things using local reasoning only, just with this substitution. And that breeds compositionality, so where the meaning of two programs is just the sum of the meanings of the individual programs. There's no like generative effects, like what we call like side effects. And the way you deal with this thing is through its many algebras. So it's obviously famously a monad. It's also like a functor and applicative and what have you. And so yeah, so let's jump straight into it and see an example of data processing using I/O. So I've got this very simple function on list, takes a list of string and returns another list of string. And what I'm doing is basically filtering on that list. So basically I want to remove empty lines and comments and mapping everything to uppercase and take the first 100. And that's good. But let's say now I want to read this list from a file. And by the way, the reason this is good is because it's nice and compositional. Every line makes sense on its own. And when I put all these lines together, the whole also makes sense on its own, and I can keep composing it with other things. And now that I read from file, I don't want to lose that property. And therefore, I want to use I/O. I don't want to have side effects if I want to read from a file. And it's very simple. I just imagine I've got this thing, and this comes from Java or in pure Scala. So I need to rough in I/O to make it referentially transparent. And then when I map, I'm describing a computation that will read the file and then do something on it, and I just do process on it. And that works. But the problem with that one is that what if the list does not fit into memory? What if your file is too big? So now, like, to make it work, you kind of need to revert back to reading a chunk at a time and doing things manually on each chunk. And it will still be pure, because you will do it in I/O with like tail recursive function or whatever. But you kind of lose this nice, filter map, high level way of expressing behavior, and that's not nice. You revert this like purely functional imperative programming, which is way better than side effecting imperative programming, but still not quite as high level and not quite as expressive and as map and filter. So let's introduce Fs2 streams then. So Fs2, like a stream is, again, is just a data type. It's a data type that represents a computation. Just like I/O, just like option, just like list. And you can see it's got two type parameters, a higher kind of parameter f and an a. And the semantics of this type is a type that will emit 0 of n values of type A, where n can be infinite. So I'm basically describing the process of emitting either 0 or 1 or multiple values, and I can also emit infinite values. And emitting infinite values is not a corner case. It's just a perfectly fine thing to do. It's handled fine, and it's actually quite useful. And I've got examples of like why would you do something like an infinite stream. And while emitting these values, it will request effects in F. And what I mean by request is, like, again, sort of describing what effects need to be performed in order to emit these values. So in the case of reading from a file, the effect being described or required is, read from file, and the values emitted might be, I don't know, the lines from the file. And what is this F? F is normally I/O. So you can imagine something like cat's I/O as the F. So in the actual code base, we actually abstract over F in most of the code base. We don't want to be too concrete, obviously. But for simplicity in these slides, it's just going to be I/O everywhere. Yeah, but obviously you can use different things. So for example, Doobie uses this connection I/O thing, sort of a transactional DB monad, and you can stick that one in there. So let's look at an example of streaming I/O. I think this sort of reads quite well, even though you're not familiar with the library. So what I'm doing, I've got this simple pure function that converts Fahrenheit to Celsius, and I'm going to use the I/O module of Fs2 to read the file. Just read the whole file, and I'm going to decode it with UTF-8 and take each line, remove empty lines and lines that are comments, and then do this Fahrenheit to Celsius conversion, put a new line after each, encode back to the UTF, and then write into a file. Now think about this. If you look at this, it reads like I'm actually reading the whole file into memory and then transforming it and then writing it back into another file. But this is not what's happening. What's actually happening is that the library is reading one chunk at a time, processing one chunk at a time, and then writing one chunk at a time. So this is happening in constant memory. And this is what we mean by streaming I/O. You don't need to read the whole thing into memory. It will do what you would have done manually by, like reading these chunks, just automatically. And we have regained the nice property we had before. Each line of this little program kind of makes sense on its own. And composing it also makes sense on its own. And now it's in constant memory. And so you don't have to trade, streaming with effects. You can have both streaming and effects and purely functional niceties in one thing. So this is like the obvious use case for a streaming library like Fs2. I've got a big thing, it doesn't fit into memory, I need to stream. And that's good. But I think just as if you think about streaming, that you think Fs2, I think the converse of that is that if you don't have streaming needs, like if your files or you don't need to use a lot of memory, then you think, well, then Fs2 does not bring anything to the table for me. So what this talk is actually about is not really the streaming aspect, which you still get, but why would Fs2 be useful even if I don't need to stream? And the reason it's useful is for control flow. So, yes, control flow. So Fs2 streams. Let's first see how to create a stream. So the first combinator is this emit thing. And emit is just describing the process of emitting a series of values with no effects. And again, nothing's happening right now. We're just creating data structures. So this stream is just going to, when compiled and run, it will just emit 1, 2, and 3. And now, obviously, we want to be able to embed effects into streams, like request and effect. So the way we do it, we have an I/O, in this case, just a simple print line. And by this constructor called eval, we say, well, create a stream that will sort of run this I/O and emit the result of the I/O. And then I've got another random combinator called repeat eval, which is basically like eval, but then does it all the time. So these two are primitives. This one is obviously not a primitive. And it's not even particularly important. I just wanted to show it to you because it's an example of an infinite stream. And we'll see how this infinite stream can be useful. So this is how you create a stream. How do you run it? So this is data structure, right? So you can compose this data structure, but at some point you want to do things. And actually, we don't provide anything to run it side effectfully. What we say is we compile it down to a single I/O. So you have I/O, which is this thing that can produce one value and do arbitrary effects, and then you have these streams. And basically, once you've done composing your streaming program, you can just say, well, I'm going to compile it down to an I/O of unit. And when I run the I/O unit, all the streaming thing is going to happen. So this assumes that all the values emitted are being accounted for one way or another, either because you are writing them down somewhere or because you're using them in other streams. And again, this is it's not the only way to run a stream. You can also run it to a list, but obviously that does not work in general because a stream may be infinite. So this is the canonical way of running a stream. So now you've got an I/O, just like your other I/Os in the program. You can compose this with I/Os that are not coming from Fs2. You can do whatever you want. And then at the very end of your program, you say main action and save run sync, and things will happen. But this obviously needs to be the last thing you do, because otherwise, this is actually side effectful. And actually, these days, we have a thing called stream app, where your main can just be a stream. So that thing is not even necessary anymore. You just build your own, your all app on stream, and no side effects inside. So it's really good. Okay, so this is how you create streams. So mainly emission and evaluation of effects, and then a bunch of other combinators to do that. And I want to discuss a little bit how do you manipulate these things? We've seen that I/O has got flatMap and attempt and things. So what do you do with streams instead? What are the operations that you can do? And here, obviously, there's a million. So what I want to do is mostly give you an intuition for how to reason about stream with two or three examples, rather than be exhaustive and tell you all the things you can do. And the intuition I want to give you is that Fs2 is designed to sort of act like a list with superpowers. So if you're familiar with how to write things on lists, that intuition carries over fairly well to writing streams, except now you've got this extra power of doing effects. You've got the extra power of doing effects, you've got the extra power of infinite things, and the extra power of lazy emission. You can emit one thing at a time. So let's see. So this is a very simple code that operates on a list. It creates a list of 1 to 100, takes the first 3 elements, and then appends 21 and 22, and then that's the result. So the equivalent code in Fs2 will be like this. And again, I'm giving you an example of an effectful stream instead. So I've got this simple I/O that's just print line whatever I pass as an argument. So this is basically, a purely functional print line, because it's just a computation that when run will do print lining. And then I'm saying, well, repeat eval print line. So now I've got this infinite stream that will basically, when run, print hello all the time. And when I do take 3, just take 3 on a list takes the first 3 elements, take 3 on a stream requests the emission of 3 elements. So what's happening, really, is that you're going to print hello 3 times. And then, just like ++ appends to lists, ++ on a stream means sort of run the first stream to completion, and then run a second stream. Just when you append on a list, you finish the first list, and then you start the second one, and it's the same thing with a stream. So when you run this thing, when you compile it down to I/O and run the I/O, you're going to see hello, hello, hello world. So we embedded effects in a kind of list-like abstraction. And I think it's fairly easy to read as well. There's no surprises there. So the next aspect of kind of stream as a more powerful list is flatMap. So if you're familiar with flatMap on a list, you can take each element of a list and then produce another list per element via an arbitrary function, and then they're all going to be concatenated together. So in this case, I'm just duplicating the element, and then 1 to 3 is going to become 1, 1, 2, 2, 3, 3. So let's see if we can do the same with stream. Again, same thing. I've got this purely functional print line. And so it's literally the same. So for each element that is emitted by the sort of the source stream, I'm able to produce an inner stream, an arbitrary one. So in this case, I'm just saying the same thing, repeat eval, which gives me this like lazy infinite print all the time thing, and then I'm just going to take 2. And here, then they get like all appended together, and the same thing happens here. And what does appending mean? It's just plus plus, as I've shown you before. So what happens here is basically, for each element, you're going to sort of produce the first stream, and then produce the second element will be produced, and you produce the second stream, and then the third element will be produced, and then you produce the third stream. Very simple. And this is completely sequential. So if you've used like reactive stuff, it's a bit weird there. Like you've got like non-determinism in their operations. But in this case, in our case, this is completely sequential. So it's just literally the same of map and then fasten. So yeah, another example. And then the third one I want to show you is a bit more interesting because it's a bit sort of weirder, I think, and it's zip. So with this, I've got 1, 2, 3, ABC, and zipping just means sort of putting sort of pairwise elements in pairs. So let's look at this example instead. So I have got same thing, purely functional print line, and this print range. So print range will sort of produce a stream of 1 to 10, and then print each element. This eval map is, again, is a non-primitive, is a derived combinator. It just means flatMap and stream eval. So basically, it's the same thing as for each if this was side effectful, because it's running an I/O action on each element of the stream. And this runs obviously as fast as possible. So the 10 elements will be emitted as fast as possible, and they will be printed as fast as possible. And then I've got this other combinator, this other stream here, which is using awake every. And awake every basically it's a timed stream, so it will emit a tick on each second. So I've got this very fast stream here that will print 1 to 10 super fast. And then I've got this stream that will do like this sort of ticked emission of like 1, of like units or whatever. So when I zip, just a zip means take the first element of this and put it with the first element of this. Zip on streams means, well, wait for one to emit, and then wait for the other to emit the same element, and sort of like put them back together. And what it practically means is that you've got this very fast stream that now is forced to go at the same speed of the slow stream, because like it emits the first element, and now it needs to wait for the other one to emit. And then it will try and emit the second element, but it needs to wait for the other one to emit the second element. And so the effect of doing this is that you get 1, 2, 3, 4, sort of timed on each second. And I think this is really nice. And the reason it's really nice is because we got a very nice separation of concerns. So I'm separating what to do and when to do it in a way that is completely compositional. This is a stream that makes perfect sense on its own. Maybe I want to test it. I don't want to wait like 10 seconds to test this thing. And this also makes sense on its own. And I can combine them together with several combinators, in this case zip, and achieve the behavior I want. And especially in this case, like if you do it with I/O, you're going to have sort of a recursive function that will like sort of print one element and then wait, and then print the second element and then wait. And that's kind of like intertwined in a way that cannot be separated. I need to sort of force together what I want to do and when I want to do it. Whereas this streaming abstraction allows me to separate things. I know that this is also an infinite stream, and it works just as well, because the thing will finish when this one finishes. Just like with zip, if one of the two lists is too long, they just get trimmed when the other one is finished. So yeah, compositionality and this high-level way of composing things, which I think is really nice. So let's look at an example. And I've got this health check API. Imagine like our system is flaky, so I'm just gonna like call this API that returns true or false if the thing is up or down. And what I want to do this check every hour. But if the check fails, I don't want to give up straight away. I want to try 5 times, and then if it's still false, then it means it's actually down. If not, it's true. So let's say I've got this message type. So message is not an Fs2 thing. It's like your application, whatever. And I've got stream retry, which takes an IO action, initial interval, a function to increase the amount of time you want to wait. So in this case, it's linear backoff, and a number of max retries. So it will try to do it 5 times, and then if it cannot do it 5 times, it will fail. And I'm just running retry check, and this will return, it will emit a single value, either true or false, with this retry. And when I map, it means map on the success case, so no errors. It will emit it true, and then I wrap in health check message. And then if there was an exception, well, not exception, a failed state, because obviously we don't try exception, it's all pure. Then I'm going to say, well, then return error message. And so I've got the logic of doing sort of this retry thing. And how do I do it every hour? Well, it's pretty simple. I do check, and then after doing check, I just append stream sleep 1 hour, and then I just repeat. So I've got another infinite stream that will just do this logic. So this logic is like very common. Like every project I've worked on had like a custom weird thing to do this. It's just 3 lines, and again, it's very nice and compositional. So yeah, I'm slightly late, so I'm going to accelerate a bit. But yeah, so the point is like declarative control flow. And what I use as a recipe for this is that you create simple single actions in I/O. Normally they will be wrapping, your impure library or whatever. And then you use stream to assemble them, sort of to weave this control flow all together. And this is high level. We've seen, map filter, and not like while m or until m or recursive, functions. It's obviously declarative, and it's composable. It's all pure and compositional. You can, build separate things and put them back together, and you can understand complicated things by splitting them into its components. And what I use as like my sort of slogan for this is that IOs are your words, and streams are your sentences. So obviously you can build when you speak, you can think about each individual word, but that's not what you do. Normally you tend to think 1 sentence at a time. And I kind of think about this in the same way. So the single individual actions, are there, but the way I want to describe my flow is with streams and with sentences. So let's get into concurrency now, because I think this is kind of what sets apart Fs2 from other streaming libraries, especially purely functional streaming libraries. So let's start by looking at what features do we have for concurrency. So first of all, stream concurrency. What is stream concurrency? What I mean by stream concurrency is the ability of interleaving multiple streams in a non-deterministic fashion. Just as simple as that. So you got stream A, stream B, and it's going to do, emitting 1 from one stream and then 2 from the other in a non-deterministic fashion. And then obviously concurrent coordination and data structures. As soon as you have this non-deterministic interleaving, you need to have ways of coordinating between concurrent streams. So we have, refs and queues and semaphores and signals and a lot of other data structures, and they're all like, pure and non-blocking. So round thread pools, obviously, just because you have multiple streams, it doesn't mean you want to have multiple threads. You only want to have a big number of streams and a small number of threads, because on the JVM, threads obviously are scarce resource. And so this works out of the box. It even works on the Scala JS, where you have like one thread. Non-blocking, same thing. So blocking on the JVM sort of takes a thread away from you, so you don't want to do that. So all our algorithms and data structures are non-blocking. So even when we say a queue blocks on the empty queue, it's not actually blocking a thread. It's just semantic blocking. The thread is free for other stuff to run on. And finally, it's resource safe. So streams normally allocate resources, open files, open sockets, and we ensure that no matter what you do with that stream, even if you can flatMap it and have all sorts of concurrent flow, we keep track of the lifetime of the resource and make sure it's closed, both in successful or in successful stream or in case of errors, no matter what you do. So you don't have to worry about the hard stuff. We kind of do the hard work for you. So why concurrency? Why is it important for a streaming library to have concurrency? So in my view, streams are kind of like logical threads of execution. In an imperative thread, you have do this, do that, and so on. Where if a stream is well, emit this, emit that, with actions. And they're kind of like nicer threads because you have combinators on the thread itself. You can say take 3, which is kind of like execute the first three instructions and so on. But obviously, since a stream is like a logical thread of execution, it only makes sense that you want to have sort of multiple threads of execution, because interleaving these logical threads can allow complicated behavior to be built. And I want this to be still declarative and composable. I don't want my properties to break when concurrency enters the picture. And I argue this is pure FP for the real world. So people always say pure FP is nice for small algorithms, but when you actually have to do databases and HTTP, then you have to go imperative. And I would argue it's the other way around. It's fine if you want to write a small algorithm with while, with no effects, if you need extra performance or whatever. But when the hard stuff comes, then you want your reasoning to be there. So yeah, this is pure FP for the real world. So let's start with the simplest example. So I've got multiple streams and I want to run them concurrently. So I got the health check example from above, from before. And I also have this other stream of Kafka messages. They've been read from Kafka, and all sorts of logic in there. I don't care. It's just a stream of message for me. And then I also have the Humble Celsius converter from slide 1, and I want that to run in the background as well. So how do I do this? The first thing I need to do is to create a stream of streams. So I create a stream that is made of this apply is just kind of like emit. So it will take any number of arguments and just emit them, and it's emitting streams themselves. And notice this drain thing here. So you can think of this. Imagine you've got a list of 1, 1, and hello. That will not compile, or it will compile, but it shouldn't compile, because they need to be homogeneous, right? They need to have the same. All the elements need to have the same type, and in this case, all the stream need to emit the same elements. So what drain does, and if you look at this, I don't care about the emission. I only care about the effects. So I want that file to be converted, but I don't care about emitting units on each line. So what I want to say, well, this stream needs to run for its effects, but I do not care about the emission of its results. So that's what drain does. Drain means run a stream for its effects, but don't care about emitting values. And so these two are going to emit message, and so the actual stream is going to emit message, and everything is going to work out. And if you're interested in this from a type system perspective, this returns a stream of IO nothing, and nothing is a subtype of everything, so it will all compile. And then with this join, it takes a stream of IO message, and sort of collapses it into a stream of IO message. So it's similar to flatten, except flatten is like the monadic operation, so it's going to be sequential, whereas join is like concurrent flattening. So you're just going to start pulling from the fastest one and sort of run this thing concurrently, and it's going to handle all the cases you can think of, like what if one stream fails, what if one stream gets interrupted, and so on. It's all handled by this combinator. So this is the basic run stuff concurrently combinator. And what I get here is just another stream. So I keep flat mapping, and I haven't lost my compositionality. This is just another stream, and I can keep going, even though this was created using a concurrent abstraction. So what I want to conclude with is kind of this example showing how concurrency is useful to build behavior. I want to build a general combinator that will take any stream, run it for a certain duration, and then stop it. So the first thing I want to do is use this interrupt when combinator. So interrupt when takes a signal, and I will tell you what it is in a second. And when this signal sort of triggers, it will interrupt the stream. So a signal is one of those concurrent structures I was telling you about, and a way to think about it is like, imagine something that tracks changes to a thing over time. So like the speed of a car. At each given time, the speed of a car is going to be a certain value, and that's what a signal does. And in this case, it's very simple. It's just a Boolean. It acts like a switch. It needs to be on and off. So once I set this thing to true, the stream is going to be interrupted. And then I want to have another stop. And again, stop takes a signal as an argument, and I want them to be both taken as an argument so that I can share the same signal. And to build this thing, I'm just going to say, well, sleep for the duration. And after sleeping, then set the thing to true. And set returns an IO, and therefore I need to evaluate to put it in the stream. So I've got this completely independent pieces of behavior. I've got something that will interrupt when a switch is flipped to true. And I've got another thing that will wait for a certain amount of time and then set a switch to true. It doesn't even know about in at all. And now to sort of put everything together, I need to create a signal, initialized to false. And again, creation of a signal is effectful, so it will return an IO, and that's why I need to evaluate. And then when I flatMap, I have access to the signal. And then I can create the out and so the runner and the out and the stopper. So I've got this thing that will like run until the switch is set to true, and this thing that will wait and set the switch to true. How do I put them back together? I cannot use ++, because otherwise, it will either run the whole thing and then stop it, or it will stop it before it even runs it. I need to do this concurrently, like at the same time. And you can do this with join, but actually this case is a very common case of having one thing that you care about, in this case, the out, and another thing that needs to run on the side. So we have a combinator called concurrently, which basically takes runner and returns runner, but also starts another stream concurrently. And so this like kind of does what you think it will do. And we can refactor it a little bit. Again, this is just purely inlining. There's no logical refactor. But I'm just saying, well, to close, I take a signal and sort of do the same thing, and then create the signal, and I'm going to take in, interrupted when the end is reached, and concurrently close the end. So I will argue that this is like super clear. And again, it's still composable. Every single piece sort of makes sense on its own. That's concurrency. And this is the way you can build all sorts of complicated behavior. And the way, for example, I've used it, I got the initial repeat eval, print line hello, which doesn't make sense. Like, why would you do it like infinitely? But I want to do it for 2 seconds. I want to print hello for 2 seconds and then stop. And see how I've got this like, sort of I've curried the thing, so it returns a function from stream to stream. We have this thing called true that takes functions from stream to stream, so that you get this nice Scala-like syntax of, sort of foo.bar.buzz. And so yeah, I repeat eval the hello, and I want to stop after 2 seconds, which reads exactly like what it does, and this is not what I wanted to do, and I'm not sure how to not do that anymore. Nice. Yes. So yeah, and so go wild. I built all sorts of stuff with concurrent Fs2, rate limiters and sort of concurrent abstractions for streaming or not streaming. Actually, the majority of my use cases of Fs2 do not involve streaming. I also happen to need streaming sometimes, but it's great even when you don't, because depending on what you do, you might or might not need streaming, but you need control flow regardless if you write code. And this gives you a nice composable high-level way of doing control flow. So Fs2 streams are great when data is too big to fit in memory, and they're also great when control flow is too hard to fit in your head. I'm not on Twitter, but you can reach out on Gitter, SystemFw, with the W. And also special thanks to Michael Pilquist and Paul Kluplasek, which are the other maintainers. And I think I've got some time for questions, so ask questions.